So this is the content, and we'll start with an introduction to IQM. So IQM is the European category leader in quantum computers with over 50 million euros in signed contracts over the last 18 months. We are the first quantum startup to have delivered a quantum computer to our customer. Our first customer is VTT, the Government Research Labs in Finland. And currently we are delivering our second system, a 20-qubit processor, to the Leibniz Supercomputing Center, LRZ, in Germany. This is a quantum accelerator product where the supercomputing center is interested in integrating the quantum computer in their supercomputing workflows. So at IQM, we deliver full-stack quantum computers with our own fabrication, with our own design tools and a control software, and one of the largest quantum engineering teams in the world. We are a spin-out from Aalto University and VTT in Helsinki in Finland. We spun out in the summer of 2019, and today we are a little bit over 200 employees. We develop and sell on-premises quantum computers based on superconducting technology, and we have secured 2 rounds of investment so far, totaling a little bit over 200 million euros. To date, we have sold 2 quantum computers to Finland and Germany, and we have deployed several other computers as part of research projects across Europe. As said, we are today a little bit over 200 employees. Around half of us have PhDs. At least 7 of us are professor-level tech leaders of over 39 nationalities today. Here you can see that about 75% of us are in technology. So we are a very science and technology-heavy organization, as any quantum computing company today should be. And also about 75% of us are located in Finland, but we also have a large theory team in Munich, as well as smaller offices in Paris and Madrid. So the way we look at the quantum computing landscape, or quantum computer sales landscape at the moment, is summarized here in our strategy, that we are today in the foundation phase. This is the stage when countries, states, universities are learning about quantum computing, are getting interested in this, and this is what we call the foundation phase, where we are commercializing early quantum computers for research and education. There's a lot of interest around the world to start building quantum ecosystems, and for that you need something to pull the people in and to show people that quantum computers are a real thing that you can use. Next step, where we need to get to, is the advantage phase. Of course, as everyone is talking about this. And for us, we believe that we can really find a fast lane to quantum advantage through co-design. And this is what the second half of my talk will be about, showing you an example of what co-design can do for us to move us forward towards quantum advantage, while keeping an eye on the fact that in the end, what we want to get to is a disruption phase with large-scale error-corrected quantum computers. So our product portfolio at the moment is shown here. Last year, we have delivered our first 5-qubit device to VTT, and this is a fully integrated system which has been benchmarked and is ready for delivery. So if any one of you would like to get one, you show me your credit card and we'll make that happen. As we speak, we are delivering our 20-qubit quantum computers. We are upgrading the VTT's device from 5 to 20 qubits and also delivering 20 to the Leibniz Supercomputing Center during next year. And at the end of next year, or early 2024, we'll be delivering a 54-qubit device to VTT. And during next year, we will also revise the product portfolio with a product roadmap showing you the future. So we're always asked about the spec. How is the quantum computer? Is it any good? Here are our numbers for the device that we have delivered to VTT. These are average numbers. So it is a 5-qubit processor on a star, 1 qubit in the middle, coupled to 4 neighbors. We have a single qubit gate fidelity over 3 nines and a 2-qubit gate fidelity over 2 nines. We're very happy about these numbers, very proud of these. I think these are a very good starting point, but of course, nothing is ever enough. So this summer, we have also then demonstrated a control Z gate of fidelity over 99.8% of fidelity, which is bringing us on par with the state of the art in the world. And this is with our new long distance trans-1 coupler. So the device coupling the qubits to each other. Typically, making it larger tends to make the gate fidelity fall, but making it larger allows for more separation between qubits, reducing crosstalk. And so we managed to show this high fidelity with this long distance coupler, achieving both at the same time. Furthermore, I'd like to highlight our Unimon qubit. There's a paper that came out a couple weeks ago in Nature Communications. There's a new qubit type, which is a resonator with a single junction in the middle, simplifying manufacturing and simplifying fabrication, and is showing very high promise for taking that next leap to bring the fidelities even higher up with this qubit type. So with that, now let's get to the co-design. To look into the future, what might the future hold? So the way we look at co-design at IQM is here, in this intersection between the application, the problem you're trying to solve, the software that you're using for that, the algorithms, and the quantum hardware that you have available for that. And we're trying to fit these three together as well as possible. So we want to pick a problem which is suitable for computation by noisy quantum computers, while using an algorithm which fits the problem, of course, but also the hardware, taking into account the gates you can do, the operations you can do, and the hardware needs to fit the algorithm and the problem requirements. So these can all be tailored for a maximally impactful device. This means, of course, that we might need to go look somewhere unordinary. So the normal recipe for building a quantum computer for a general purpose QPU is to take your favorite qubit, put them on a square lattice or maybe hexagonal lattice, and then you operate single and 2 qubit gates on that. That's all fine, but when we're looking to start doing these optimizations, actually there's a large toolbox with all these building blocks that we can take. We can take qubits, but they can be different types of qubits. Various kinds of superconducting qubits are out in the market. We can look at qubits, so multi-level systems, or even resonators. These are all things that we have, as physicists, we have in our toolbox. We can connect them on different topologies. It could be a square lattice, star topology, something irregular, whatever is fitting your problem in the best way. And there could be many meanings to best. And then finally, we could look at the operational level. How do we operate the device? Do we do digital computing with single and 2 qubit gates? Or do we do analog evolution of the device? Or some sort of hybrid digital analog computing, which is its own research field. And now we need to start looking at how do we put these building blocks together? How do we build a beautiful castle out of these building blocks? And that's now the topic of the final part, which is the co-design chip for nanoscale NMR simulations. So this is a paper that we published about a month ago in Physical Review Research called Co-Design Quantum Simulation of Nanoscale NMR. Here we are looking at the problem of creating safe and efficient contrast agents for MRI imaging. We have an algorithm layer where we look at the structure of the algorithm, giving us this sort of star topology, which requires resets on the central qubit. And then we look at how do we realize a processor like that, a star architecture chip. Now, the problem we're setting out to solve is developing safe and efficient contrast agents for MRI imaging. If you've been in an MRI image ever, you might have had to swallow some contrast agent or be injected with contrast agent to improve the image quality. This is usually based on gadolinium, which in the medical jargon has low biocompatibility. It's a poison. And if you're a sick patient who needs frequent MRIs, you might not want to be exposed to gadolinium over and over and over again. So there's a proposal that we can replace the gadolinium with nanodiamonds, which are inert. They have high biocompatibility, but we need to be able to polarize the nanodiamonds. We need to get them magnetized. And if we stick them in a magnetic field, that's not going to cut it. It's not enough contrast. So there's a proposal that if you have nanodiamonds with NV centers, you can drive the NV centers with microwave drives to polarize them and transfer the polarization into the nuclear spin of the carbon-13 in the nanodiamonds. This way you could create highly polarized nanodiamonds, but we need to figure out how to drive the NVs. There could be many, many situations, many, many drives, and this is what we want to bring onto simulation away from the experiments. And the problem structure is like this. We have an NV center, which is interacting with all these carbon nuclear spins, which could also be interacting with each other. And that is the thing we want to simulate. So a quantum algorithm that looks at this protocol will have to have this sort of structure where we initialize our state of the qubits, which one qubit represents the NV and the other is nuclei. Then there's some time evolution. It says your trotterized evolution. It could be some other technique. And then we will reset the NV we'll reset it, we will initialize it again in the polarized state and transfer. Reset, transfer, reset, transfer. And you can already tell that actually we are simulating non-unitary dynamics, which is also a little bit non-standard for quantum algorithms. And once we look at the time evolution block, it will also have this sort of structure, no matter which algorithm you use, in fact, where you have 2-qubit gates between the NV and the nuclei. And this is there by design from the problem. And this then might already start to remind you about a star, that, hey, if we have a star topology, then we will not have to do any swaps. On a square grid, you would have to be transferring the information around the chip to make it, to do all those gates. But with a star topology, you don't need to do any of those. So our first thought was, hey, let's take transmons. We use transmons all the time. These are the best qubits around, and let's put them on the star. Turns out you can't do that. The central qubit will not be a transmon anymore if you keep connecting more and more qubits to that. You will make it a linear resonator with bad properties. And anyway, the qubit is very small, so connecting many to a very small point is difficult. So our solution for this is to now go into this co-design toolbox and look at what kind of stuff do we have available to us. And our solution is to replace the central transmon by a resonator. So resonators are nice, they are big, so there's plenty of physical space to couple our qubits to the central resonator. Resonators can have very high Q factors, so they can be very favorable with very long lifetimes. And we believe this design should be scalable to several tens of qubits, whereas with a central transmon, we're limited to less than 10 qubits coupled to that. Here we should be able to go to at least 50 qubits coupled to a resonator. And finally, we dug even deeper in our toolbox and found the quantum circuit refrigerator, which is some of the founding IP at IQM, which is a device to reset a qubit to a resonator in nanoseconds or 10 nanoseconds. So this is faster than single or 2 qubit gates even. It's ultra fast reset, which is needed in this algorithm with several steps. So the results are here. So the question is, like, what does this buy us, right? This chip. And we've been simulating on 6 qubits, 6 noisy qubits, and comparing a square grid with the star topology. And we want to find the NMR peaks. We want to find the central frequency of the NMR peaks. And here on the right-hand side, you're seeing the delta peak, which is the error in the peak frequency that we get from the simulation. And we see here that the blue line is the co-design chip, the red line is a square grid. And to achieve the same fidelity, the same error in the peak detection that would take 4 nines of fidelity on the square grid chip, only takes 2 nines of fidelity on the co-design chip. So we are relaxing the hardware requirements by 2 orders of magnitude here for 6 qubits. And when we scale this gap will only grow. Of course, both will get worse, but the gap will grow. So we will really be relaxing the hardware requirements, the fidelity requirements, quite considerably on that. And today, this is the state-of-the-art fidelities, 10 to the minus 3 errors. And so you can see that this error in the peak frequencies drops by at least 2/3 when we change the topology into this co-design chip. So in summary, I showed you a little bit about IQM's history, what we do, what kind of technology we have. We talked about co-design, and I gave you this example of creating a co-design chip with several new elements, using a resonator as a computational element, and using the quantum circuit refrigerator as part of the algorithm to reset the qubits. Thank you very much.
We still have few minutes for Q&A if you have any question.
Yeah, yeah, interesting. The co-design comes from requirement from problem and
right.
And software to this hardware side, right? So is there maybe in your vision, right? Maybe there will be another interaction from hardware side to
Bingo.
Yeah. Can
Bingo.
you comment on that?
Yes, that's something I forgot to mention. Exactly. So now we have designed a star topology chip that was inspired by this MRI imaging problem. Now the question is, what can we do with that? Right? So now we can come back up from the hardware level to the applications. And of course, what we have designed here is not an MRI simulation chip. It's simulating highly connected spin systems. And so, or in general, highly connected systems that need a lot of interactions. We're minimizing the number of SOP gates by more than 90% in these larger chips, more than 20 qubits. And that's really going to make a difference for systems that have high connectivity. So there's really now we can start taking this in many directions. So even though we talk about quantum ASICs and application-specific chips, maybe it's more where we get the inspiration from, and then we can go look, where does this apply?